Hello, how's it going? I was thinking maybe I should make some more sort of beginner-friendly content. Why not? It's super important, it's easy content, it's foundational, and it's good exercise for me to explain these concepts as well. What I want to look at today is something called an affine transform, and I'll give you the short answer. Okay, so the goals today are to understand what is an affine transform and why are they useful, I guess, or how to find their inverses. So here's the short answer. An affine transform is a transformation which does not change the fundamental shape or the fundamental size of an object. So let's say I have my mesh here. It represents a block. One sort of affine transformation is a translation. So if I move it from one point to another point, fundamentally it has the same area, the same shape. Another example is a rotation. So if I were to rotate this mesh, yeah, it's rotated, but it has the same fundamental shape. Its area is still the same. An example of something which is not an affine transformation is if I were to apply a shear. So if I were to sort of stretch this off and apply a shear, the area of the shape would change. That is not an affine transformation. Another example is scaling. So if I were to scale this shape, its area has changed. That's not an affine transformation. I can apply non-uniform scaling. That's another example of a non-affine transformation. But given that we have a translation and a rotation, potentially also a mirroring, but we'll leave the mirroring for now. Any combination of those forms an affine transformation. Now, why are those important? Short answer, affine transformations are important because they are very easy to invert. There's a quick formula. Okay, so now on to the meat of the presentation. So at this point, I'm going to be talking around the topic. Sometimes I'll be talking below the target level of the topic. Sometimes I'll be talking above the target level of the topic. We've got the main content down, so that's fine. Just settle in, enjoy it. So transformations in OpenGL are represented with matrices. Let's say we have a point which is represented as a vector. It has an x and y coordinate. A general transformation of this point would be to multiply it with some sort of vector. The dimensions of the vector are 2 rows and 2 columns. The dimensions, of the matrix, the dimensions of the vector are 2 rows and 1 column. Inner dimensions match, and the resultant has the outer dimensions. So we need something that has 2 rows and 1 column. So I don't know what the coefficients are in the matrix. I'll just keep them super general. Some unknown real numbers. The way this multiplication goes is we have a linear combination, a times x plus b times y. And then for the second row, another linear combination, c times x plus d times y. Now looking at that, we can say, what sort of transformation is that? Well, it really just comes down to what the numbers are, a, b, c, and d. So, for instance, if I were to perform I'm thinking this up on the spot, let's say a scale transformation. I could sort of work backwards here. I could say, let's say I want to scale x by a factor of 2, y by a factor of 3. I just came up with those numbers. So I want my result to be 2 times x and 3 times y. We say, all right, what numbers would we need in our matrix? Well, we have, here we have 2 times x plus no y, nothing times y. Here we have 3 times y plus nothing times x. Okay, fair enough. So how could we represent a rotation? Rotation's pretty important. That's an affine transformation. Well, this is sort of a tricky thing to wrap your head around. But what we do is we start with the basis vectors I and j. And we say, what are the images of those basis vectors under the transformation? So what I can do, I'll do this with a dotted line. Imagine taking this set of basis vectors I and j and rotating them by some angle counterclockwise. So that's my image of I. This will be my image of j. And we can draw a little diagram. We've rotated them by some angle. In order to find the components of these vectors, I'm going to break them down. So we have a right angle triangle here. I'm going to express I dash in terms of the original x and y coordinates, in terms of the original I and j basis vectors. So this is some angle. We have a length of 1. We know that because it's a basis vector. And so the length of this will be by trigonometry. We have the hypotenuse times cosine theta. In other words, cos theta is the length there. It's the adjacent side to this angle. Over here we have sine theta is the opposite side to this angle. Okay. And now if we were to construct we look at the first vector here. This is the original I vector. When we hit it with that transformation, it needs to go to this I dash vector. We know the I dash vector in the I. This is a little funky. The x component of the I dash vector, I'll say that, needs to be cosine theta. The y component needs to be sine theta. So that is the image of the I basis vector under rotation. Now, for j, we do the same thing. We break it down into a right angle triangle. So this is my j vector here, and I need to find my j image, my j dash. So this is a little funky, but for the x component, we see the x component is on this side here. The x component is opposite to the angle, so that would be saying sine theta. But it's also pointing off into the negative x-axis, and so I'm going to put a negative sine theta there, because sine theta is the length of this side, but its orientation is off to the negative x. And then if we look on this side, the y component of it is the adjacent side, so that will be cosine theta. And so the image of the j vector is given here. Now, still haven't answered our question, have we? That was, what was the original matrix? Well, we sort of have answered our question, because this vector here, this matrix, is the identity matrix. So really it's saying like some unknown times 1 makes this matrix. And so this is actually our rotation matrix by the angle of theta. Okay. So this matrix, we can think of it as, a 2 by 2 matrix, a collection of real numbers. We could also think of it as a collection of vectors. Each of these columns is a vector. And furthermore, there's a property that a matrix like this has. It's called an orthonormal matrix, or orthogonal matrix. Orthonormal, same thing. And what that means is that these two vectors are orthonormal. They form an orthonormal set. That is, this vector, its inner product with a vector that isn't itself is 0, and its inner product with a vector that is itself is 1. Now I'm going to drill into that a little bit. What is an inner product? Like I said, this is a beginner-friendly video. I'm not assuming any prior knowledge. I hope it's fun. Okay, so the inner product is also sometimes called the dot product. You may have seen this in math, but let me take two vectors, u and v. Okay, the inner product of these two vectors, or the dot product of these two vectors, is the summation of the element-wise products. Just like that. If this was higher dimensions, we keep going, there'd be more terms. This has the property that it's also equal to the magnitude of one times the magnitude of the other times the cosine of the angle between them. Now this cosine of the angle between them starts to lose meaning as we pop into higher dimensions. I mean, we're never going to go into higher dimensions in graphics programming, but just for life knowledge, when you go into 4 dimensions, 5 dimensions, and stuff like that, this loses its geometric meaning and starts to become a measure of how independent two vectors are. Two vectors are dependent if they can zero each other out. So these two vectors, if I subtract one from the other, maybe scale one a little bit, I can get them both to 0. These vectors are independent. If I subtract one from another, it'll change a little bit, but there's no way to use this horizontal to remove the vertical size from this second vector. And these vectors are orthogonal. That is, they are completely independent of each other. There's no part of this vertical vector which has anything in common with this horizontal vector. And so when we get into higher dimensions, if we have a measure of 1, that's saying they are completely parallel, the same thing. They're completely dependent on each other. If they have something that's between 0 and 1 but not inclusive on either end, then they have some dependence on each other, and if the cos of their angle comes out to 0, that means that they hold completely different information. There's no redundant information in those two vectors. But this is going a little deep. Anyway, if we were to look at that rotation matrix again, I want to prove or show that its columns are orthonormal. So if I take, what did I have? Cos theta something like that. And then I'll multiply that with its transpose. And let me explain why I want to multiply with its transpose. Back when I looked at this exercise, I could have actually recast this as this element here is like taking this first row times this first column, and that can also be expressed as the dot product. And likewise here. So if I see, let me say, sort of run out of space, but the dot product or the inner product of two vectors, that's also completely equal to the transpose of one times the other one. Mathematically, it'll work out. The formula will work out to be the same thing. And so that's what I'm doing. Whoops. Back here. I'm trying to show that this matrix times its transpose will work out. So I'll take the transpose here. Okay. So for shorthand, I'm going to start using C for cos theta, S for sine theta. Now if I look at this multiplication, I have cos times cos. So we have cos theta squared, plus down here we have sine times sine. So we can also think of it as this is this transpose times the original. In other words, it's this vector dot with itself, this vector inner product with itself. And now let's look at this one, inner product with the first vector. That's negative cos times sine plus cos times sine. So you can see what's going to happen there. And then likewise, we'll look at this vector, inner product with the other one. So we'll have negative cos times sine plus cos times sine. And then down here we'll have negative sine times negative sine, which is sine squared, plus cos times cos. And this comes out to 1, 0, 0, 1, which is the identity. Now there are two super important things that we're getting here. First of all, we're showing that this matrix is orthonormal. Its columns dot product with themselves are 1 and anything else is 0. And secondly, as an aside, we're also getting the property that this transpose of this matrix forms its inverse. And that's super important in affine transformations, because if we have a rotation matrix, it tells us that all we need to do is take the transpose of that rotation matrix, and that's its inverse. So now for another concept, which is how do we represent translations in matrices? Because so far we've just been using multiplication of matrices. And the answer, I'll give it away, is we add an extra dimension which is just a placeholder. It's just there, information that we might need. So let's say we have a points x and y coordinates, and I want to translate it to x plus something, y plus something. Okay, now I look back at the matrix. I say, what do I need? For the top row, I need 1 times x plus, no y, plus a. How do we do that? This is sort of a trick. I have a times 1. I'm going to insert a 1 there in the bottom. Extra information. Now, for the second row, all right, no worries. We'll have no x info there. We'll have y, so 1 times y, plus some number times 1. And then what I want to do is I then want to have it set up so that after I apply this transformation, I still keep a 1 in the last row, just if I would need to apply any further transformations. And so the way I keep that is I just have the identity in the last row. So no x, no y, 1 times 1. Cool. Okay, so just like with the rotation matrix, we tried to work out some property. We tried to work out what its inverse would be. Another pretty decent question is how do we work out the inverse of a translation matrix? So what is it that we multiply it by a translation matrix, and we get the identity. Okay, you can probably imagine, just think of this geometrically. What's the opposite of translating by some amount? It's translating by the opposite amount. So if I look here, I say, okay, well, if I look at the first row, I want something times 1 plus something times, oh yeah, sorry. So I'm looking at, yeah, that's right. I'm looking at this column here. So I have 1 times 1 plus, it really doesn't matter, plus it really doesn't matter, because this information is all zeros. Then I look here, I have really doesn't matter, plus 1 plus who cares, to get a, oh, whoops. I may have just may just have to redo that. Easy to get tripped up with these exercises. Let me go the other way, actually. Let's verify it. So I'll put in the opposite translation, and let's verify that this works. So here we have 1 times 1 plus 0 gives me 1. And then here I have, yeah, 0 times 1, 1 times 0 is 0, 0 times negative b, so this comes out to 0 as well. And then here we have 0, 0, 0. Excellent. Now here we have 0, 0, 0. Good. And then 0, 1, 0, 0, 0, 0. And then finally we have 1 times a plus 0 plus 1 times negative a. That does in fact make 0. Then we have 1 times b plus 1 times negative b makes 0. And then 0, 0, and 1 times 1. Excellent. Cool. All right. So. I've been talking about how affine, let me just give a quick little summary. So an affine transformation is 4-dimensional. It's a 4x4 matrix. It has the following properties. The upper 3x3 represents a rotation. The columns of this matrix, this 3x3, should be orthonormal columns. If they were generated by an axis rotation formula or a multiplication of those, totally fine, it should work. Down here, we want this to be just the identity. We always want that there. And then this last column should be the translation. That's 3 rows, 1 column. So this will be the ABC, XYZ translation. Now, reasonable question is, I said that these have a quick inverse. Why do we care about a quick inverse? Well, let's look at finding the inverse of a 2x2 matrix. I've got some general 2x2 matrix. I want to find something such that when I multiply it, I get the identity. Doesn't matter if it's a left inverse or a right inverse. I can use Gaussian elimination to find the value of these unknowns. So I break this down into a system of equations. I have a times some unknown plus b times some unknown produces 1, and then using the other column, produce 0. C times some unknown plus D times some unknown in the first column is 0, and in the second column is 1. I'm sort of not giving a rigorous treatment of Gaussian elimination here. You can go look that up. It's publicly traded information. But the goal is to switch this around so that I have the identity on this side, and then whatever is left on this side will be the inverse of the matrix. So the first thing I need to do is zero out this element here. And the way I'm going to do that is I'm going to say, okay, row 2 becomes, I'll take A times row 2 minus C times row 1. So then here I have A times D minus C times the above. And then here I have to do it on the right hand side as well. A times 0 minus C times the row above. And then, yeah, A minus 0. Okay, cool. So then, likewise, I need to zero out this element. So now I'm going to say you can see how you can see why I chose to do a 2x2 example, not a 3x3. Gets messy. Okay, so where was I? Now working on the right hand side. So here I've got AD minus BC times that 1. But then I've subtracted B times this element here. So plus BC. That's one whole thing. And then here I've got minus A times the below. Then here I've still got that minus C and that A. Now, of course, these ones are going to cancel out. And then I'm going to divide everything by A in the first row. So I'll say row 1 is row 1 divided by A. And that will produce Oops. So if you have any experience with matrices, you'll see that this is basically looking correct. I just need to divide everything by this factor AD minus BC, and we get something like the inverse is 1 over AD minus BC times this matrix, where we have swapped the A and the D and negated the B and the C. But that's not my point. My point is if you look at all the work we needed to do to get there, and that's just for a 2x2, this is a very simple case. A 3x3 gets a lot bigger. It's a lot more work for the GPU to do, and it's a lot more work if you're going to do that inverse on the CPU and then send it over to the GPU. So let's look at, hopefully I've made a case for the importance of having a quick inverse. Okay, so inverse of a 4x4, an affine transformation. Well, what we can do is individually invert these components. So I say, what's the inverse of a rotation? It's the transpose of a rotation. What's the inverse of a translation? It's the negation of that translation. And I'm going to just do a little quick demonstration here. So let's say I'm just going to put some columns here. So these are the basis vectors for the rotation component. These are 3x1 columns. I'll just put them like rotation 1, rotation 2, rotation 3. They're just basis vectors. And then A, B, C will be the components of my translation. So what I'll do is I will transpose the rotation components. And negate the translation. Alrighty, and so this will be a little messy. By the way, if you'd like to see more detail on this, I've got a video in my OpenGL with C++ playlist talking about transformations, where I go into more rigorous derivations of these sorts of things. But yeah. So just verifying that this comes out to the identity. Here, if we think geometrically, we have like this vector dot with this vector. Now for the first part, we have the inner product of a vector with itself, and we've shown that these rotation vectors are orthonormal. We're taking that for granted. So that will come out to 1. And then we have some number times 0 does not contribute anything. And then likewise, if I look at this vector here with this vector, well, these vectors are not the same. By the orthonormal property, their inner product comes out to 0. Then if we look right down at the bottom, we have some vector dot product with 0. Doesn't matter, because element-wise, the sum of products with 0 will all be 0. And then here we have 1 times 0. So that comes out to 0. And then likewise, for this first row, different vectors, so that's 0. For the second row, same vector, so that's 1 by orthonormality. And then 0, same trick, 0. Then here with the R3, we have 1, different, 2, different, 3, same, 0. And then right down here for the last one, we have got I've just missed something here. It's a little more complicated than simply taking negation. What this will be is this will actually be Let's say it's unknown. Actually, no. I'm thinking. Let me set this to little funky here. What I'm doing is I'm saying, instead of just being negative a, that ABC forms what I'm going to call the translation vector, the displacement in the A, B, and C. Now if I look at this first bit here, I have this R1 transpose times the translation. So this is contributing the dot product, the inner product between R1 and the translation. And so to negate that, I want to have negative R1 dot the translation. And then likewise here, so that will come out to 0. Likewise here I have R2 dot with the translation. And so this last component should be negative dot between the translation and R2. And then similarly right down the bottom here, we look in here, R3 transpose times the translation, so that's the inner product of these two. We need to negate that, so we need to bring in the negative inner product between the two vectors. And then right here we have 0, 1 times 1. It comes out. Okay, so that went probably longer than it had to, but I think there's some benefit to covering the topic at a number of different levels. The key point is that an affine transformation is a combination of a rotation and a translation. So anything where I can throw the mesh down like a piece of paper and spin it around, move it, combinations of those are affine transformations. The benefit of an affine transformation is they have a closed form inverse. We transpose the rotation, the upper 3 by 3. We take the dot product of the translation with the rotation vectors. And I know that I'm talking in circles. That's okay. And then I guess the next sort of important part is, why might we want to have a nice formula for the inverse? Well, besides the fact that it's quicker, we sometimes need to find inverses of affine transformations. For instance, if you've got a camera and that camera is hanging out in space somewhere, looking at the world. Okay, so here's the origin of the world. Here's the camera not at the origin, at some angle or whatever. The camera had some sort of model to world transform that put it out there in the world. But if I can quickly work out the inverse of the camera's transformation and apply that to everything in the world, that will map the world back into the camera's frame of reference. This is super common in producing what's called look-at matrices for viewing things as we move cameras around the world in graphics APIs. Okay, so I hope you enjoyed that. I hope that cleared some things up. Let me know if there's anything else you would like explained. I like these pen and paper things. Anyway, all the best. Have a great weekend. Have a good time. And I'll see you soon. Bye.